In the previous video, we created the mesh for these parts. So if you haven't already seen that video, you might want to go back and check that out first. In this second video, we will set up the simulation with all the necessary keywords in LS-PrePost. First off, let us create some materials for our parts. We want to create a rigid material for the flat plate and an elastoplastic material for the square tube. We open the keyword manager, which is where you will find all available LS-Dyna keywords. You can here toggle between model to see your model's existing keywords, or all to see all available keywords, including already existing ones. To create a material, we first go down and expand the material section. And we first choose material number 20 for the rigid material. Just double click to open that. We first click new ID, get the new material ID here. And we then specify density, Young's modulus, as well as Poisson's ratio, even though this is a rigid material, since these parameters are used in contact definitions. When creating a rigid body, we specify degree of freedom constraints on the material card itself. So we therefore toggle on the center of mass constraint. We choose to constrain the rigid body in all translational degrees of freedom as well as all rotational degrees of freedom. If you see here, I'm going to put 7 here, as well as a 7 here. You then need to click first accept and then done in order to make sure that the keyword is actually added to the model. As you can see, if we switch over to model, and there you have it, material 20 is now there. So moving on, for the tube, we will go with the versatile material number 24. We find here, and we specify material parameters for a generic steel. Oh, something like that. I should probably explain that LS-Dyna doesn't have any system of units, so it is therefore up to you as a user to keep track of the numbers that you're putting into the program. And in my case here, I'm using tons for mass, millimeters for length, seconds for time, Newton for force, and megapascals for stress. And that is the reason why, for instance, the density here might come off as a bit weird looking with this small number. Now we go to our part definition to assign these newly created materials. Another thing which all parts need to have is a section card specifying what element formulation is to be used. And if you know what keyword you're looking for, you can find them very quickly just by searching for them. So in this case, the keyword we're after is called section_shell. And if you hit the enter key, you're taken to the keyword directly. We'll create one section card for the square tube and the plate, as well as one section card for the square end plate. Let's use the default element formulation 2, which is a Velichkov-Tsai formulation. And we'll also increase the number of through thickness integration points to 3. We then specify a thickness for the shell element by entering desired thickness at T1 and pressing enter to autofill the other 3 options. As I said, we also create a keyword for the square end plate and set that to 3 to match the part number. We'll just increase the thickness there to 2. We then assign these newly created section cards the same way as we did with the material cards. That is, by going to the part keyword, and then you see that there is a box here for section ID. And remember to click accept to actually make sure that the change goes through. Now, this is 1/4 of a square tube, so naturally, symmetry conditions must be specified. The easiest way to apply such boundary conditions is to specify them on a set of nodes with the keyword called boundary underscore single point constraint underscore set, for which we first need to specify a node set. One option is to add such a node set keyword called set node list, and then specify all the nodes directly. However, this is not a very nice way of working, since we have no idea what the node numbers in question are. A much better option instead is to create the node set graphically with the create entity tool, which we find up here. We here go down to set data and choose the node set. Next, we have to toggle on to create a new set. If we first create a node set for the symmetry condition in the y direction, that is for the rest of the tube here, then we want to select this entire edge here. In the selection tool, we choose by edge, and we also check this box here to propagate the selection. We then select an element edge here. You see that it also selects all the other nodes in this on this line here. We'll just select the rest of the line here, as well as this. We can give the node set a title. Then we just click apply to create it. And for the symmetry in the x direction, we do the same thing. We also give it a fitting name. With the node sets done, we can create our boundary conditions by using the keyword called boundary underscore single point constraint underscore set, which you find the keyword manager up here under boundary single point constraint set. Now we just have to pick our node set. So we start with the symmetry in the y direction. We have to constrain the degrees of freedom accordingly. So since this is the y direction and there's the rest of the tube here, we have to put a constraint on the y translational degree of freedom, as well as these two rotational degrees of freedom, since these are shell elements that we're dealing with. And we'll also create one for the symmetry in the x direction, which of course we here must change these. Oops. So it should be like this then. The next step is to also create boundary conditions for the square end plate, which we will use to crush the tube against the wall here by means of a prescribed displacement. We therefore create a node set as before. And give it a name. Now let's put a boundary condition on these nodes here in the same way as before with the boundary underscore SPC underscore set. Just create a new one and we choose the newly created set. And we'll constrain it in all degrees of freedom except for the translational degree of freedom in the set direction, which is the direction that the movement will be in. So we can't constrain that. Now, let us create a prescribed motion for this end plate here. And we do so by using the keyword called boundary, prescribed motion set. There. Then pick the node set we recently created. And we need to specify what degree of freedom this movement will be in. And since this is a, the tube will be crushed against the wall in this direction. So that is, as you can see, we should put a 3 here. Have it as a set translational degree of freedom. And in the next box, we have to specify whether or not it's a velocity, an acceleration, or a displacement. So number 2 there. Now, you can see that we need to give the keyword a load curve ID, but we don't have one, so we'll first have to create a curve. First, let me just accept this here. And you can create a curve with the keyword called define_curve, which we will find under define curve. And here you can just specify points of the curve. And this simulation will run for 0.02 seconds. So therefore, I'll create a ramped curve up until then. If we first just insert this point here, and then second point. And now, for numerical reasons, load curves should be defined for a longer period of time than the end time of the simulation. So I'll therefore just insert an arbitrary third point here. And if we accept this, you can also plot it. You see that we have this ramped curve here. Now we can go back to the prescribed motion and select this new load curve. Select it here. As you could see, I defined the curve so that it reached an ordinate value of 1. It is up to you to decide if you want to normalize your curves in this way, or if you prefer to create them with the actual values directly. But I find it is easier to work with the normalized curves and use scale factors. So you can then use the same curve definition for several things. And it is also much quicker to just change a scale factor later if you want to have a different value. And I want this square end plate to move 80 millimeters in the negative direction. So therefore, I put this scale factor here to -80. There is also another way of creating curves, and that is by using the curve generation tool found in the top menu under Application, Tools, and there you have it, curve generation. With this tool, you can very easily create smoother curves with more points. You can see if we try and recreate the previous curve, we get a much smoother curve this way. Moving on. Since we want something to happen in the simulation, not just see the parts pass through each other, contact definitions must be created. First, I'll create a tied contact between the tube and the end plate by using the keyword called tied nodes to surface offset. If you search for that one, and it is found under contact, tied nodes to surface offset. So this one here. Now, don't be alarmed by the vast number of options on the contact keywords, for we'll only use a few of them. Under Surf A type and Surf B type, you select what type of entity the contact applies to. And here we will choose to apply it on the part level, since that is easy. Set these both to 3. And then I will set the tube as surf A and the end plate as surf B. We also need a contact definition between the tube and the flat plate. And for this, we can use the automatic nodes to surface contact. See, automatic nodes to surface. We'll also apply this on the part level. I'll set the tube as surf A and the plate as surf B. And I'll also add a static coefficient of friction, like so. As the tube is crushed, it will start to buckle and come into contact with itself. So I'll therefore define a keyword for self-contact as well. And the automatic single surface works well for this. So this works by just specifying one part here, the A, surf A type. Let's have a static coefficient of friction here as well. It is possible to name your simulation in the title keyword. So let's do that and give it a descriptive name. Now you will see this new title in the top left corner of the screen. You must always specify the end time for your simulation using the keyword called control_termination. So let's do so. As I mentioned earlier, the simulation will run for 0.02 seconds. And next, since this is an explicit simulation, I will also add a keyword to control the time step. In which I specify the time step scale factor, which scales down the critical time step so that the simulation has some safety margin rather than computing right on the verge of becoming unstable. The default value is to use a scale factor of 0.9, which is sufficient for most applications. I will also add a keyword to avoid hourglassing. And this we can do by the control hourglass keyword. And this one, the control hourglass, it applies to all parts in the model. Lastly, we will specify some output that we want to have from the simulation. And first, let's add a database_ASCII option card. And here we will check the global statistics box, which will give us information about model energies, among other things. And then I will also check the box for resultant interface forces, as well as the one for cross-section forces data. Now, to specify the time interval between output for these, you can type in a number at each box, or you can fill in a number at the top here. And then by pressing the Enter key, you can see that it automatically fills in all of these boxes. Let us also add a database extend binary keyword. And here we will toggle on the strain flag to make sure that the plastic strain data is written to our results, since this is not done by default. I'll also show you how to create a cross-section plane, which we will be able to get data from since we checked the cross-section forces box in the ASCII option keyword previously. So this cross-section can be created with the keyword called database cross-section plane. And if I just show the model here, so let's have the cross-section be, say, 12 millimeters in from this end here. Then we would put the set coordinate of the tail here as 12. And then we just need to specify a normal vector for this plane. So this value doesn't really matter, nor does this. So I will just put some numbers there. And with that, we have all the necessary keywords for the simulation, and we've reached the end of this video.